So the notation used is a slightly different from the slide before, but it's very much related, obviously. So what is different now is that the agents have a value for maybe one of the slots, for example. And in addition to that, they also have an arrival time. So an arrival time is when they are available in the market, and the departure time. So the latest time they can get a slot. So essentially what it's saying is, for example, this agent here, so this agent here arrives at time 3 and at time 4. So essentially he's only interested in having either a slot at time 3 or a time 4. He's not interested in having a slot at any other time. This agent arrives at time step 1, but has to leave again after time step 3. So he's essentially interested in having a slot, one of these 3 slots, and then the same, similar for this agent. So essentially what we're saying is that this is a bit similar to the setting we had before, in that in a way the preferences change, right? So at this point the agent has 0 preferences for a certain slot. Here, this slot, or any of these slots, is worth 10 to this agent, and then here the preferences become 0 again, because the agent is not in the market, so you cannot benefit from these slots. I'll give you examples of what this means in practice in a bit. So what we have here is some sort of, so the type really is the arrival, departure, and the value. So it's not just the value anymore. And agents can manipulate all of these values. What is usually assumed in mechanism design is, so in online mechanism design, is that agents can only manipulate in a certain way. So that whether that makes sense or not depends on the domain, the setting where you apply this kind of mechanism. So the agents can only report a later arrival, not an earlier arrival, because if the agent reports an earlier arrival, but he's not there physically, how can he receive the items, right? So that's kind of the idea. And he can report an early deadline, meaning he can leave the market earlier. Then maybe he could have stayed in the market longer, but he decides to leave earlier. Then it's true. So you can see this here. So maybe A and D are his true arrival, or his earliest possible arrival is latest possible departure, but he can only reduce this. So he can say report a later arrival or early departure. So he can reduce his availability in the market, but not increase it. Okay. This is what the report would be. And he could obviously manipulate his willingness to pay or a value for having a slot, say, in this market. Okay. So maybe I should start with an example here. So the example that I'll be going through is one that I've done some research, quite a bit of research in, is looking at electric vehicles, right? Or the smart grid in general. So we've got a certain devices, for example, electric vehicle, who need electricity. So the battery needs to be charged. Okay? So at some point in time, the car arrives at home, for example. So at that point, the car can be plugged into the grid. It needs a certain amount of electricity. So maybe it needs 3 units. It doesn't really care when it gets it, and as long as it's before he leaves the market. So there's a departure. So the departure is basically when the driver meets the car, right? So they have to depart the market. And as soon as they depart the market, obviously they can't participate in the market because they cannot receive the resource, which is in this case electricity. That makes sense as an example? Yeah. So I'll go back because so far what I've talked about is this value here. And what does it represent? So it's not necessarily true case that you have a value for 1 unit. It could be that you want maybe multiple units. For example, with the electric car, maybe you want 10 units. Okay? So you're interested in having 10 units. But you have a certain amount of demand that you want in order to drive to work. For example, 10 units of electricity will give you enough electricity to drive to work the next day. So if you have less than 10 units, you cannot actually use the car because it's not, your battery is not charged far enough to go to work. If you have more, that's okay, but you don't really need them. Okay? So what we can say is that this value is obtained at a point where you have received a sufficient number of units. So what is usually looked at in mechanism design, at least in the online mechanism design setting, is the simplification where you only have your values represented by one value, essentially. So E is a single dimensional value, or a scalar. But it can be fairly generic in the sense that even if you want a bundle of items, so it just assumes that as long as you want a certain bundle of items, and if you get that bundle of items, then you receive that value. If you get more than the bundle of items you wanted, you still have the same value for them. If you get less than the bundle of items that you wanted, then you have a value of 0 for them. Okay? So this is kind of a bit of a restrictive model that's being looked at in the online mechanism design literature. So this is kind of a formal way of saying that. So we looked at before X was the set of possible allocations. Li is a subset of these possible allocations, which is agent I's interesting set. So the agent is interested in this subset of possible allocation. If the outcome for agent I is in that set of allocations, then it gets a value of Vi. If it's not in that set of interesting allocations for this agent, it gets a value of 0. So, for example, in combinatorial options, maybe you come across this, so where you have multiple items, say Matthijs gave examples of the fridge, the freezer, and the washing machine, or the fridge, the dishwasher, and the washing machine, right? So that could be the auction of these 3 items, and maybe you only have a value for either the fridge or maybe either the washing machine or the dishwasher, right? Because you have one space, so you have a value for getting one of those. Okay? But you have no more value if you also get the fridge as well. So you don't get an additional value. So this means that your preferences can be kind of summarized in one value plus this set of interesting sets. So what do you find interesting? So what we could model with that is, for example, this electric vehicle setting, where the agent wants a certain number of units to charge its car, so say 10 units. As soon as it has those 10 units, then it gets utility of Vi. If it gets any less, then he gets 0. If he gets more, then he still gets Vi. Okay? So that's the kind of model we'll be working with for the moment. So these kind of situations are actually special case of what's called single-minded theaters, where an agent is only interested in one specific bundle. Does that make sense? Now, one of the assumptions that's often made in online mechanism design, but we're going to relax that assumption later on, is that the interesting set is known. So that means that the mechanism designer, the system or the center, knows what the agents would like, but it doesn't know what its value is for that bundle or this number of units. And it also doesn't know its arrival and departure. And then we relax this later where we assume the interesting set is not known. We also look at why it's a problem if it's not known, why certain mechanisms no longer work. So we look at some examples where the incentives are working. Okay? So just to make it a bit more clear, so what kind of goods are we looking at here? So we assume that there's time, and over time there's going to be resources available. So maybe you can think of at every time slot, the good is going to be auctioned off. So maybe time slot 1 is going to be washing machine, time slot 2 is going to be the fridge, and then time slot 3 is going to be the dishwasher. Okay, so you could see different goods being allocated. Or you can think of the electricity example. So at every time step, there's so much electricity that can be auctioned off because there's certain network constraints. So the electricity is not unlimited because the neighborhoods have certain constraints that makes that you can only supply a certain amount to each house. So what we can look at is 2 different types of goods. So some perishable. So this means that I have to allocate goods now in this time slot, or they'll be wasted in the next time slot. So that you could think of is the electricity. So suppose you have some solar panels on your house, right? Or maybe they're joint solar panels. So solar panels are maybe owned by a community of houses, and at every time step you have to decide who gets what electricity. Okay, so there's a fixed amount of supply available, and maybe you don't even know what the supply is in the plant, and you have to allocate that to agents who are interested in the market at that time. So if you want to charge this electricity, renewable energy to, say, electric vehicle, then you can only allocate it to electric vehicles who are plugged in at that point in time. Okay? But then unless you store it, right, you cannot keep electricity, so this electricity is wasted. So the other kind of application is, for example, if you have computers that are running certain tasks, you want to allocate resources, computational resources, to these tasks. So if you don't use the CPU time at one time slot, it's going to be wasted. So you can't actually keep it and then allocate it to the second time slot. Okay. So that's the kind of domains we look at. So these are called perishable. Or you can have persistent, so the goods, so the white goods that we talked about, but also, for example, if you're selling some kind of concert tickets. So concert tickets are also perishable in some sense, because obviously after the concert they're useless, but you can still allocate them at other time slots as well. So it's not necessarily that they expire immediately. Okay? So we often denote that by here. So here you have this timeline, and at every time step, certain amount of resources, which I call supply, are going to be available, and we have to then allocate at every point in time the resources that are available to the agents who are present in the market, or who say they are present in the market. So this is the electric vehicle example, so in a little bit more detail using the concept we've just discussed. So the interesting set here for the electric vehicles is the amount of electricity needed to sufficiently charge the battery, whatever that means. Maybe fully charge it, or sufficiently charge it for the agent to travel to work. Obviously, electricity in this case is a perishable good, so unallocated electricity is kind of wasted, unless we can somehow store it. What does the reported arrival mean? Okay. So, you say your electric car, you come home with your electric car, and then you plug your vehicle in immediately, and then you only unplug it when you actually need the car, right? So you have the maximum time window available, which means that you allow the mechanism more flexibility to allocate some resources. Because the problem with electric vehicles, that's why there's a lot of research on it at the moment, is that if everyone arrives at the same time, at 6 o'clock, say, at home, everyone plugs in their vehicle at the same time, then there's not going to be enough electricity to charge all the vehicles immediately, and you get blackouts. Okay? So what needs to happen is somehow this electricity needs to be scheduled. So some people get the electricity immediately, and other people get the electricity a little bit later. And how do we decide who gets it later, who gets it now, and who doesn't get it at all? Okay? So that's the kind of questions that we can answer with this online mechanism. So suppose that you are telling the mechanism, I need it by 8 o'clock tomorrow morning, because I'll unplug at 8 o'clock tomorrow morning. And the mechanism decides not to give it to you, whereas if you say, I need it now, in 2 hours' time, right, and the mechanism does give it to you instead, then obviously you're going to misreport, say, instead of needing it tomorrow morning, I need it now immediately. So this is kind of misreporting. So you could unplug your vehicle earlier, or tell the mechanism you're going to unplug the vehicle earlier, and so in that sense you are misreporting your departure time from the market. So if it's in your advantage to misreport it, to arrive maybe a bit later, then the selfish interested agents will do so. Okay. So misreports, for example, delaying plugging in of the vehicle. So you arrive at home, you decide, if I arrive, I plug it in now, it's going to be too expensive, for example. I'm not going to plug it in. I'm going to wait a bit longer. That's kind of a misreport. Okay. So we want the mechanism to design a mechanism that truthfully elicits the the true arrival and departure time. And that's the mechanism decide who gets what at what time. Okay. So how are we going to do that? Right? That's the question. So what kind of mechanisms could we have that allow us to incentivize this kind of, say, electric vehicles to be truthful? So we've already seen that VCG and dynamic VCG optimizes and determines the social choice function of VCG needs to be optimal. Okay? So actually, it was optimal, but actually it needs to be optimal. Otherwise, VCG is no longer incentive compatible. However, optimality is not always necessary to achieve truthfulness. So what we can do in single valued domains is actually there's another condition that we need to satisfy instead of optimality. So there are other mechanisms out there except VCG. Okay? So we can get truthfulness with other mechanisms that are not VCG. Okay? That should surprise you. Okay? Because Matthijs has been saying, no, this is the only mechanism. Right? So why can we have? What's the thing that was so particular about VCG that makes it useful? Yes?
Agents can come and go. Physical agents can come and go.
No, not even that. Even if agents are in the market at the start, we can still have truthful mechanisms which are not VCG. So it was a bit tricky because the key thing with VCG is that it's the only mechanism that is truthful and efficient, right? Maximizing social welfare. Okay? If we drop the necessity that the social welfare has to be maximized, so it's not that we're maximizing something else instead, as you kind of suggested, but maybe it's suboptimal. We could get other mechanisms that are still truthful. Okay? So these mechanisms will be inefficient. Okay? The problem with VCG is if you have a big problem, it takes a lot of time to compute. So these problems are usually empty hard if you have a combinatorial option. So they can't really be solved within reasonable time often if they get quite large. So sometimes we have to have a suboptimal solution because we can't compute the optimal solution. And then we can't use VCG anymore, but there are other mechanisms. Okay. So just to be clear, so VCG is the only mechanism, or sorry, not VCG. So the class of Grove's mechanisms, okay, is the only class of mechanisms which are at the same time truthful and efficient. Okay. So if you want an efficient solution, you have to use Grove's mechanisms. If, on the other hand, your solution doesn't have to be efficient, you can use other mechanisms. Okay? And we'll see what mechanisms they could be. Okay? And obviously, the dictatorial one is an example of a non-efficient mechanism. In the randomized dictatorial already. Okay? So we saw already an example. It's possible, but there are other mechanisms for the case where we have transfers. We can do that, but not necessarily optimal. So in fact, there's a condition which is a necessary condition in order to get truthfulness, which is called monotonicity. Okay? And this is where it gets a bit tricky. So monotonicity, what does that mean? So monotonicity means it's all to do with the social choice functions. But we're not looking at payments at the moment. So the nice thing is with these kind of mechanisms is that say, let's design a social choice function, and then let's compute the payments which match that social choice function. Okay? So it's not necessarily that we have the optimal social choice function. We can have other social choice function, and then once we have that, we can find the payments that belong to that function. And as long as the social choice function is monotonic, it's usually okay, but not always. Okay? So what does monotonicity mean? So this is about the social choice function. So it means that there are certain restrictions on the social choice function, such that suppose that the type theta I is allocated, so he receives his interesting set, right? He receives the bundle he wants. If he reports theta I, then if he reports a type which is better, a higher type, okay, he should also be allocated. Okay? So it could never be the case that if you report a worse type, you get allocated, but if you report a better type, you're not allocated. So a better type should always get more, essentially. What does a better type mean? It means, obviously, if you have a higher value, if you're willing to pay more for something, you should get more than if you're willing to pay less. Okay? Should be obvious, right? If you arrive earlier than someone else, you should get more items than someone who arrives later. Right? So given everything is the same, right? Everything else remains constant. Okay? If you arrive later, or so you depart later, again you should get more than someone who departs earlier, everything else being equal. Right? And that's simply the idea of monotonicity. So if you have more flexibility, so you arrive earlier or you depart later, so you have more flexibility, or you're willing to pay more, you should be allocated more, or you should be allocated with high probability, or whatever. So you should get a better deal in terms of allocation. So we're not talking about transfers here. In terms of the allocations, you should be better off. Okay? If you are a higher type. So this is formalized here, which is this bunch of equations. Okay? You don't have to really understand everything, but let me just show you what I mean here. So suppose, what I'm introducing here, so we had this social choice function here before already, but what I'm introducing here is this omega, which is kind of a realization of events. So this is with hindsight. So as I said, so new agents come into the market, and we assume the mechanism doesn't know anything about agents coming into the market, but maybe agents know about other agents entering the market. Okay? So they could anticipate other agents entering the market, and they could then maybe manipulate based on this information that they have, but the mechanism doesn't have. Right? Because what we want is still dominant strategy. We're looking here for dominant strategy. So regardless of what other agents do or no. So what we have here is this realization. So after the fact, given all the agents have entered the market, now it's the end of the day, say, we want a situation where if I had a better type than someone else, in a sense, I get more, I get allocated, or allocated more, or